All right, everyone, get ready because we're diving into some seriously cool physics today. We're talking quantum physics. You guys gave us some seriously interesting research to dig into. And let me tell you, it does not disappoint, basically. We're going to try to break down this experiment that's giving us a peek into how some of the universe's fundamental forces actually work. And spoiler alert, they don't always act the way we expect. Don't worry, no physics degree required here. We'll make sure it all makes sense.
Absolutely. We're going to lay it all out for you, not just what happened, but why it's a big deal.
Okay, so imagine this. We're trying to wrap our heads around how particles interact at the absolute smallest level. We're talking those fundamental particles, quarks, gluons, ones, and that crazy strong force that's holding everything together. But here's the thing. This stuff is so complex, even our most powerful computers struggle to simulate it accurately. And that's where quantum simulators come in.
It's like having a tiny universe right there in the lab.
Okay, so before we even get to the experiment itself, maybe we should take a second to unpack this whole quantum simulator thing. What exactly are we talking about here? And maybe even more interesting, what is it not?
Well, for one, it's not some high-tech computer game. As fun as that sounds, think of it this way. A quantum simulator is like a system that operates on the rules of quantum mechanics, and we can actually use it to kind of copy the behavior of other quantum systems, the ones that are way too complex to study directly.
So, like using a model airplane to understand how a 747 flies, except instead of aerodynamics, we're talking about the universe's fundamental forces.
Yeah, exactly. Regular computers kind of hit a wall when it comes to the weird world of quantum mechanics,
Hmm.
where things can be in multiple states at once. A quantum simulator,
Right.
it's built on those same weird rules, so it's like they speak the same language.
So cool. So, how did the researchers actually do this then? I mean, it sounds like they used lasers to break apart a string made of atoms.
You're on the right track. They use these things called trapped ions, basically just really tiny electrically charged atoms held in place super precisely. And these ions were like stand-ins for quarks, those particles governed by the strong force.
And I'm guessing the lasers were like the tools to move these tiny particles around and make the conditions for this string breaking to happen.
Exactly. Like imagine a microscopic tug of war.
Huh.
Using lasers, they were able to set up the conditions for the string breaking.
Now, this is where it gets really cool because they weren't just breaking these strings randomly. They wanted to see if something specific would happen, something that could either prove or disprove our current understanding of these forces. They were looking for the Schwinger mechanism, right?
You got it. And that is a seriously cool concept. Imagine a vacuum, not your household one, but a place with zero particles, totally empty space. The Schwinger mechanism basically says that if you apply a super strong electric field to this vacuum, you can actually make it generate particles out of basically nothing.
Hold on, wait. Empty space can give birth to particles if you just zap it with enough energy?
Yeah, pretty wild, right? So the researchers were trying to see if this wild phenomenon would happen when they snapped their tiny atomic string.
Okay, and did it work? Did they see what they were expecting?
Well, here's the thing. The string did break, yes, but not in the way they were expecting at all. And this is where things get really interesting. Instead of seeing particles popping out all over the string, like the Schwinger mechanism suggests, they saw something totally different.
Okay, now you have to tell me, what did they see?
They saw these particles starting to appear at the edges of the string first, like it was fraying, and then they spread inward.
Whoa, that's definitely not what anyone was expecting. So does this mean our understanding of these fundamental forces, like the strong force, needs to be reconsidered?
It definitely throws a wrench into things. This unexpected string-breaking behavior suggests that maybe there are other mechanisms at play, particularly in these carefully controlled quantum environments.
Okay, so much to unpack here. We've talked about this mind-blowing experiment simulating string breaking in a quantum simulator, and we've touched on those unexpected results. But the big question is, what does this all mean for us? Why should we care about a few atoms snapping in a lab? Well, stick with us for part 2, because we're going to unpack the larger implications of this research, and trust me, it's going to blow your mind. So before we, really dig into what this unexpected string breaking thing means, we started to talk about the so what.
And it's a big one.
It really is. This isn't just some abstract physics thing, because getting a handle on the strong force, that's like the key to understanding, well, everything. I mean, we're talking nuclear physics, cosmology, maybe even totally new technologies we can't even imagine yet.
Yeah, it's true. Like take nuclear physics, for example. The strong force is what holds those protons and neutrons together in an atom's nucleus. So if we could really understand how it works, especially at these crazy high energy levels, Who knows what we could do? We could have breakthroughs in things like nuclear fusion.
So instead of splitting atoms for energy, like with fission, we could actually fuse them together, just like the sun. Clean, limitless energy.
Exactly. It could totally change how we think about energy.
That's incredible, but it doesn't stop there, right? What about cosmology? I mean, right after the Big Bang, those forces we're talking about were calling the shots. So, this new insight into string breaking, does that mean we might have to rethink how the universe even began?
It's possible. It's like getting a clearer picture of the universe's baby pictures. And it's not just about the past. Think about the future. We might be talking about technologies we haven't even dreamed up yet. New materials, new ways of manipulating matter.
It's like opening a door to a room full of inventions we can't even comprehend right now. Okay, so let's dig a little deeper into the experiment. The paper you shared mentioned something called confinement, which honestly sounds a bit intimidating.
Don't worry, it's not as scary as it sounds. Basically, confinement just means that certain particles, like those quarks we've been talking about, they're never found alone in nature. They're always bundled up together inside other particles, like protons and neutrons.
So they're always playing hide and seek. But if they're always hidden, how do we even know they exist?
That's a great question.
Oh,
We've figured out they exist through experiments like the ones they do in particle accelerators. It's kind of like smashing two watches together really hard and then studying the broken gears and springs to figure out how they worked.
that's one way to figure out how a watch works.
You get the idea. Physicists smash particles together with a ton of energy and then analyze the pieces that come flying out. It's how they figured out that quarks exist, even though we can't actually see them directly.
Wow, that's some seriously impressive detective work. Okay, so the paper also mentions that they used a specific type of quantum simulator for this experiment, a chain of trapped ions. What's so special about that setup?
Trapped ions are great because they give us a lot of control, and they have what we call long coherence times, which basically means they can hold on to quantum information for a relatively long time, which is really important for these kinds of experiments.
So it's like having super steady hands, but at the quantum level?
Exactly. Plus, we can use lasers to manipulate them really precisely, which lets us create those virtual charges and strings we've been talking about.
So they built a tiny universe in the lab with its own set of rules. That's amazing. But they still had to get creative to simulate this particular system, right? They used something called virtual static regions. What are those and why did they need them?
Ah, good question. So we can't perfectly recreate an infinite system like the universe in a finite space like our quantum simulator, but we can get pretty close. These virtual static regions are kind of like clever tricks to make the string seem infinitely long, even though it's actually limited by the number of ions we're using.
So, like those infinite scrolling backgrounds in video games, they make the world feel huge, even though it's actually just a loop.
Exactly. By controlling the ions at the edges of the chain in a specific way, they essentially trick this system into behaving as if it were part of a much larger string.
That's really clever. Okay, so they create these virtual boundaries and then bam, they see the string break in this totally unexpected way. But how do they even analyze that? The paper mentions something called a perturbative analysis. What is that and what does it tell us?
Perturbative analysis might sound complicated, but it's basically a way for physicists to break down really complex problems into smaller, more manageable chunks. It's like a mathematical magnifying glass.
So they're searching for clues at the quantum level.
Exactly. By looking really closely at how the particles interact and how the energy is distributed in the system, they hope to figure out what was causing this weird string-breaking behavior.
Did they find any answers?
Well, their analysis definitely gave them more information. It looks like instead of particle-antiparticle pairs appearing uniformly, they mainly popped up at the edges of the string and then moved inward.
Like a domino effect. This is all so fascinating, but we're actually running a bit short on time for this part.
We are.
So let's take a second to gather our thoughts and get ready for the final part of our exploration. When we come back, we'll try to wrap up this amazing journey into the world of string theory, so stick with us. Okay, so we've talked about this experiment, this totally unexpected way that string breaking happened, but the big question is, so what? What does it all mean?
Yeah, it really makes you think.
Right.
Like, on the one hand, it just shows how much we still don't know about the universe. We're
Right.
talking about the very forces that made everything we see around us, and we're still finding new things about them.
Like the universe is reminding us that it still has some secrets.
Exactly. But it's not all just mystery either. This discovery could change everything, how we think about nuclear physics, cosmology, even lead to new technologies.
Okay, so you mentioned nuclear physics before. Can you explain how this new string breaking thing might affect that?
Sure. Remember nuclear fusion. That's how the sun gets its energy, right?
Yeah.
Atoms fusing together and releasing a ton of energy. Well, the strong force is what controls that whole process. So if we can understand the strong force even better, thanks to this experiment, maybe we can finally figure out how to make fusion work here on Earth.
So instead of just imagining a future with clean, limitless energy, we might actually be able to make it happen.
Exactly.
That's incredible. But you also mentioned cosmology.
Right. Think about the Big Bang.
Hmm.
In those first few moments, everything was controlled by these fundamental forces we're talking about.
So this string breaking discovery, it could change how we understand the very beginning of the universe.
It could. It's
Eh,
like we're getting a clearer picture of the universe's baby pictures.
That's amazing. I mean, it's mind blowing, really, that something happening at such a small scale could tell us so much about the entire universe.
It is pretty incredible. And it just shows how important it is to keep asking these fundamental questions, to keep exploring, even when we don't know what we'll find.
Because those discoveries, those unexpected results, those are the things that can really change everything.
Absolutely.
Well, I think that's a good place to wrap up our deep dive for today. We've covered some seriously mind blowing stuff, this experiment, simulating string breaking with a quantum simulator, and all the potential implications. Thanks for joining us, and keep those questions coming.